So I think we're going to go ahead and get started. Hopefully everybody got some ice cream, which is quite good. And next up, we have Ishan from MoveWeb, and he's going to talk to us about building the fastest PWA. So, Ishan.
Okay, hi everyone. I'm Ishan. Thanks TJ for the introduction. You can reach me on Twitter at IANAND, and this is how to build the fastest PWA. So I'm going to talk pretty fast because we've got a lot to go through. But before I jump into it, it's important for you to understand the context by which myself and my colleagues come at this problem. I work at a company called MoveWeb. We are a development platform and infrastructure for developers and IT teams that enables them to easily deliver sub-second site speed. That is, websites that load in under an instant. You can think of us as kind of like a CDN for the modern era. For apps built with React, Angular, Vue, and using PWA technologies, as opposed to, when CDNs first came along, they were built for when we had, HTML with just basically a sprinkle of JavaScript, whereas today we're building apps that are almost entirely all JavaScript. And a lot of our clients are in e-commerce, travel and hospitality. And one of the ways we deliver speed for our clients on our platform or one of the things they use is React Storefront, which is our open source PWA framework that you can actually go download right now, pwa.moveweb.com. And a lot of the best practices we've learned from our customers go back into this framework. So it's got a lot of kind of best practices under the hood to get you up and running really fast. So a lot of stuff I'll talk about, although it's applicable to any other React app, they're already kind of built for you in this framework. Okay, so if you walk away from this talk with only 4 things, I want it to be these. The first is that speed is the number one value proposition for PWA. The second is that you're probably measuring site speed incorrectly. The third is that solving speed is actually a full stack problem. It's about the front end, it's about the back end, and also it's about the CDN, which is often very forgotten. And if you want to get the fastest speed possible, you need to coordinate all 3 of those layers together. And then finally, I'll talk about a bunch of techniques. But the best techniques you probably are not already using are proper cache management, server-side rendering, predictive prefetching, and AMP. Okay, I said earlier, speed is the number one value of progressive web apps. And that speed is amazing. We can finally break the 1-second barrier for user perceived performance in most cases. Unfortunately, it doesn't always come easy. And unfortunately, a lot of the hype and excitement about PWAs is as a replacement for native applications. And that's a very limiting view to look at PWAs. There's only about 5 million native applications on the iOS and Android stores. There are 2 billion websites out there. In fact, if you try to graph them, you can barely see the native apps. They're a blip. So PWAs aren't just for apps. They're for any website that cares about site speed. And it may seem like an academic point, but let me make it really concrete. If you go to your boss and say, hey, let's do a PWA, it's going to feel to a lot of non-technical folks like tomorrow's technology, or it's about your app strategy. Instead, if you go to your boss and you say, hey, let's deliver the fastest site possible, and we're going to use PWA technologies to get there, it's a much easier discussion to have. Because when you talk about site speed, there's a very clear ROI in probably your KPIs, whether that's pages per visit, visitors, or conversion rate. And it's a very easy way to get the conversation going of PWA and gets everyone aligned around the table. Okay, the other thing I said was that you're probably measuring speed wrong. So I'm going to spend a good portion of this talk talking about the proper way to measure speed before we talk about how to achieve it. So historically, we used to focus on what some call quantity-based metrics. I sometimes call them network-based metrics. Things like the total download size of the page, the number of requests on the page. And these had a lot of fit as metrics for how fast the site was when we were dealing with multi-page apps. But when we moved to single-page apps and progressive web apps, they are misleading. In fact, they'll actually penalize some things that actually improve performance. So prefetching, for example, will increase the number of requests, but it's actually making the overall experience better. So what's much better is to use perceptual metrics, things like visual complete time or first input delay, which measures how interactive a page is. There's a lot of perceptual metrics out there. I'm going to focus only on 2 of them today. Those are largest image render. It's got a cousin called largest contentful paint. It also goes by the name last painted hero, or LPH, and speed index. So I'll talk about speed index first. I'll talk about the motivation. I don't think I have time to talk about how it's calculated. But the intuition behind speed index is it starts with another perceptual metric, which is visual complete time. How long does it take for the page to render above the fold? And then it goes a step further, and it tries to reward pages that progressively render. So in this diagram, you can see both of these 2 pages load in 1.5 seconds for their visual complete time, at least above the fold. But it's clear that the one on the top is a better user experience. The one on the bottom, you're waiting with a blank screen for a long time. There's a study, by the way, that came out and rated the frustration the user feels when they look at a loading page on their mobile device to equivalent to a horror movie. They actually asked people to rate pain scales, and loading web pages and horror movies are basically neck and neck at the top. And so clearly the one at the top is better, and speed index will give that a better score. Lower is better. For last image render and last contentful paint, the intuition here is that usually the largest graphical element tends to dominate the user's psychological perspective of when completeness of the page works. So think about it this way. When you browse a news article, or if you browse, say, a product page on an e-commerce site, when that product image shows up or when that banner image shows up for the news article is when you psychologically feel like, yes, the page is there. In fact, if you load the page and you had all the text, you could read the article, but that image wasn't there, there'd be a slight like, it's not quite there yet. And that's the intuition behind largest contentful paint and largest image render. So here's an example. You can see on the left, what's happening is the green shaded area is what the largest contentful paint is at that particular point in time. And here we're starting at FCP, which is the first contentful paint. And you can see it's just that little green thing in the upper left. And then for the next 3 screens, the headline is actually the largest contentful paint, even as other parts come in. And then finally, we get the hero banner image, and that's the largest image on the page, or largest content on the page, and it's actually achieved its LCP, and that's the final LCP time when that shows up. Another benefit of largest contentful paint and largest image render is in a context like a publishing context. So you've got a news article that maybe has an ad at the top. Speed index would have penalized that ad for taking a long time to load, but actually ads are kind of the thing you might want to late load to let the rest of the page be interactive. So this is another reason why LIR and LCP are really good metrics. Now, not all of the perceptual metrics are good, and I'm going to focus on one of them called TTI, or time to interactive. So what I have here is a very simple website, not even a React app. When I click on it, it counts how many times the page was clicked. The key thing I want you to observe is it only took like less than a second for that page to be interactive and respond to my clicks. On the other hand, if you go to Lighthouse, and just so you know, I sped up this video right at the Lighthouse run so that you don't have to wait for the entire Lighthouse runtime. You'll see, it might be too hard to see out in the back, but you can see it flagged in red that time to interactive as 11 seconds, so just over 10 seconds. And clearly, it was well interactive, 10 seconds before that. So what's going on? Well, let me get Google Slides back to normal here. What's going on here is time to interactive is a heuristic. It's really trying to measure interactivity, and the best metric for that is something called first input delay. What happens is when the user clicks on a page, it measures how long does the page take to respond. The problem is that Lighthouse is a simulated environment. There's no user in the flow. And so what they did is they sat down and they tried to come up with some properties about the page behavior that might indicate whether the page was responsive or not. And it looks at 2 things. At the top, it's looking for what it calls network quiet. Basically a window of 5 seconds when you have no more than 2 GET requests running. And then it looks as well for what it calls CPU quiet, which is no more than no long tasks. A long task is something running for 50 milliseconds or more. And what I did in my sample, besides having really simple code that just indicates how many times it was clicked, was I added this code. You can see at the top, I'm just using XHR. and I'm firing off a request, and it's doing no content changes to the pages, no processing on return. So it's not interfering with the page interactivity a lot. And then 4 times a second, I'm basically firing off a few of these requests. And what's happening is I'm running afoul of this network quiet sense. And the problem is that being network quiet isn't necessarily correlated to whether the page is interactive. Now, it's true if your page is not interactive, then it's probably going to run afoul of TTI, but there's a false negative problem here. You can have a page that is not network quiet and still interactive. So what are some of those things that I've seen in real life websites where this happens? Analytics is a common one. It could be something like polling. And then prefetching, which is actually an attempt to make the entire user experience better, could run afoul of TTI, because once you start that prefetching going, TTI is going to say, oh, your network's not quiet, and it'll take a long time for it to say your page is interactive. Okay, so we talked about metrics. Let's talk about tools. So there are 4 tools I'm going to briefly cover. The first one is Google Lighthouse. Lighthouse is probably the most popular performance measuring tool, not necessarily because it's the best, but because it's so easy to use. It's right there in your Chrome browser. And it's useful for measuring, first contentful paint and speed index. But it has some problems. The first is score variability is an issue. Developer on one machine may get a different score than another. If you've got some Chrome extensions running, if you've got other stuff in your tabs, or if you've just got a really slow running process on your machine, like Zoom is a classic example, it could change your Lighthouse score. So I know some companies that work around this by having a dedicated machine just for Lighthouse. I know one company that they have a machine just for Lighthouse. It just sits there, but twice a week QA goes and runs Lighthouse on it and emails the report to everybody. The other problem with Lighthouse is that it has an arbitrary weighting for that performance score. That number that you see there, 94, that is a weighting of a bunch of other perceptual metrics. And unfortunately, the largest contributor in that weighting is TTI, the metric that I feel is the least accurate of the perceptual metrics. So my recommendation is actually to not give a lot of weight to the performance score, look at the components of it, and then decide if they're relevant to you. And then finally, the other problem with Lighthouse is it can't measure browsing speed. Okay, the next one is Page Speed Insights. This is a website you go to it used to be on Think with Google, now it's on developers.google.com. You enter a URL, and it gives you some performance characteristics of your site. It's actually an amalgamation of multiple tools, so it'll run Lighthouse a bit for you. It'll also pull data from something called Chrome User Experience Report. What this is when users are browsing the web on their Android phones with Chrome or on their desktop with Chrome, Chrome is actually taking performance data about how that actual page performs, anonymizes it, and then sends it back to Google to analyze. And you can actually pull this data down yourself if you want to look at it. One of the problems with PSI is that it's a 30-day moving average when it gives you results. And so if you're in a situation where you're actually A/B testing performance solutions and you roll something out and the next day you want to see if it's improved your performance, don't go look at PSI because it's just a 30-day moving average. You're going to have to wait a month, so it's going to slow you down. So it's not good for that use case. Sometimes the recommended actions it gives you actually may not improve your performance score, so you kind of have to use your judgment there. And then the last problem with the data in Chrome User Experience Report is it doesn't know how to measure browsing speed or browsing at all in the context of a single page app. And they've acknowledged this issue on Twitter. Basically, the problem is Chrome User Experience Report doesn't know when your page has changed in the context of a single page app. And so this has 2 end results. The first is Chrome User Experience Report isn't capturing browsing speed. So it's not going to reward you for having a faster browse speed. The second thing is your number of page visits in Chrome User Experience Report could go down. So if you go from a non-PWA, a multi-page app, to a PWA, and you're looking at your data in Chrome User Experience Report, you'll see less data because it actually stopped recording after the first visit. Web page test is another popular solution. You go to webpagetest.org, you enter your URL. This is one of my favorite tools. This is the tool I rely on a lot. It's got a lot of great metrics. It has last painted hero. It has speed index, a lot of perceptual metrics. It has a lot of the older quantity-based metrics like total page size. I would not pay as much attention to those. It does have some issues with variability, not as much as Lighthouse. But you should do multiple runs. The most you can do at once is 9. So I'd recommend doing that if you can wait for it. I have noticed, especially if you're using speed index or visual complete in a browsing speed context, it can get confused as to when visual complete starts and when a transition starts. So manually verify metrics with the film strips if they look off to you. The nice thing about web page test, though, is it can measure browsing speed, and we'll talk about that in a bit. The last tool is real user monitoring. If you're not familiar with this, basically JavaScript code runs on your site and records performance data as users are browsing your site and sends it back to your server to analyze. This is one of the only ways you can actually measure what TTI was trying to achieve, which is first input delay. And so you can directly measure it because now you've got a user clicking on the page. You can also capture a lot of network metrics now are being exposed via JavaScript, like time to first byte, which you couldn't get historically. Some gotchas are the accuracy depends on the specific tool. Even if it records accurately, you want to make sure it's going to display the information as a histogram because you want to look at all this aggregate data across all your users as a histogram rather than a single number like you do when it's a synthetic measurement. Browsing speed measurement is also possible with RUM, but it usually requires some kind of integration to get the right metrics. Two caveats on simulating network throttling. So a lot of these tools will simulate a slow network in order to capture mobile performance. The first caveat is make sure you're using the settings that reflect the distribution of connectivity of your actual users. And a great source of this data is the Chrome User Experience Report. So here's the Chrome User Experience Report for Walmart.com, and you can see that 90% of the users are actually on 4G. The other caveat is that various tools use different algorithms for throttling, and they all vary in accuracy. The one built into web page test is very accurate, as is any type of operating system level network throttler. And then, ironically, the one in Lighthouse has more than one, actually is less accurate. It's actually got a mode where it doesn't even slow down the page. It actually runs it at normal speed and then tries to extrapolate what the performance would have been had it been simulated as a slower connection. Okay, so I talked about the importance of these tools that don't measure browsing speed and the ones that do. Why is browsing speed important? Well, two reasons. First, browsing is a significant part of your user's journey through your website. So here, for example, is numbers for e-commerce. These are numbers from Wolfgang Digital, their KPI survey for 2019. Average e-commerce site load time, average e-commerce site pages per session, and then how long the entire session is. If you do the math, 20% of the user journey is basically spent waiting, and most of that is browsing speed. So if you can improve browsing speed, you've really improved the user's experience significantly. The other thing is that in the context of a multi-page app, the browsing page lifecycle and the first load lifecycle were very similar. The only difference was really whether those resources were cached or not. But in the context of PWA, you have a completely different page lifecycle. And so what you want to do is you want to break your techniques into first load techniques and browsing speed techniques. And then you need to measure both of those separately to make sure your techniques are improving one or the other. So there are two ways to measure browsing speed that I'd recommend. The first is using web page test, WPT. If you go into the advanced settings, you can use web page test scripting. And the scripting language is fairly simple. It's basically keyword, space, then some command or argument to that particular command. The template goes kind of like this. Basically, you run log data 0. That tells it, hey, don't track anything right now. I'm just setting up for my test. Then the next thing is you navigate to the page that you want to measure the transition from. That's this line right here. Then give your page some time to settle if you've got some type of prefetching or anything else on the page that might need it. You may want to try warming your cache if it's relevant to your metrics. And then use log data 1 to turn on metric tracking. And then finally, you trigger a click. So this command exec and wait, it basically takes the stuff after it and treats it as JavaScript that it just runs in the context of the page. So this is really just JavaScript that does a query selector, finds the anchor tag, and generates a click on it, and then you're off and running on your metrics. The other way to measure browsing speed is through RUM. I'm going to talk about using Firebase RUM because it's free. So you can go out and use this tomorrow in your own apps, no charge. Thank you, Google. This code comes from how you do it in React Storefront. You might have to make a few changes in another framework. The first thing we do is in component did mount, we include Firebase. And by the way, we're including it here in component did mount so that it not importing it directly ES style, because React Storefront is server-side rendered, and we don't want to pull this code in the server-side rendering. We want it only client-side, hence when component did mount runs. Then you'd put your configuration information you can get from the Firebase portal. Then you initialize your Firebase monitoring. And then you basically need to capture when your router state change happens. This line is specific to React Storefront, but basically you wait for kind of before the navigation change is just about to happen, and then you tell it to trigger a function, in this case start trace. The body of that start trace is basically really simple. You're basically going to say, hey, I've got a new type of event. I'm calling it a navigation event. It's got some attributes, in this case the page, the location that the user is navigating to, and hey, start tracking some metrics on this thing. And then the only thing you have to do next is figure out when do you tell it to stop tracking that event. You don't want to do it when your router says you're done, because your page probably isn't finished rendering. What you want to do it is in component did update, but that can be called even when the page is not truly finished rendering. So this will depend a little bit on your framework or your application. As it turns out, in React Storefront, there's a really helpful property called loading that lets us know when we're actually done loading. That's this right here. And then you use that, you call trace stop, then you delete the trace, and you're done. OK, so we talked a lot about measuring speed. The 4 key takeaways I want you to walk away with are that the single best metric for measuring speed typically is last image rendered or last painted hero. But check your film strip, see what works for your use case. Measure browsing speed, not just the first page load. And then use network settings that match your user distribution. And then use both web page test and real user monitoring as the tools that I would recommend. OK, let's talk about performance techniques. So I'm going to break techniques, as I talked about earlier, on accelerating first load and those that accelerate browsing speed. OK, the first thing you want to do is minimize your bundle sizes. And the best way to do this is to look at their size and then use a bundle analyzer to see what's in them and see what needs to be removed or replaced. There are 2 popular tools for using this, Webpack Bundle Analyzer and Source Map Explorer. If you built your app with, say, Create React App, Source Map Explorer is the one that's easier to work with. And don't just run on your machine, add it to your CI/CD process. So one of the things we actually do in our platform for our users is every time they generate a build, we run a Webpack Bundle Analyzer, and they can just go to any historical build and just see what was in that bundle and see what the total size was as what was contributing to it. It's a great way to track changes. Just out of curiosity, how many people regularly use a bundle analyzer? OK, show of hands. And how many people actually use it in their CI/CD, so it runs automated? Great, OK. So after you've kind of just whole cloth removed or replaced bundles, the next kind of optimization is tree shaking. This removes basically dead code, unused JavaScript code from your bundle. That'll give you a faster download time and hopefully a faster parse time as well, although shorter code doesn't necessarily mean faster. It's implemented by your JavaScript bundler. In fact, Create React App, for example, already has it for you. But you need to help it figure out what to remove. So for example, if you've got a module here on the left, and then you import it using one of the syntaxes on the right, that'll pull in all of that code. And then you're basically relying on uglifying to hopefully find and remove code, which is a little less effective. If you use this syntax, you're telling it specifically what you need from that module, and it can be a lot more intelligent about what it bundles and removes kind of the dead code from it. So as I mentioned, most frameworks you use have this out of the box for you, but it's only usually there for the production build. So Next has it, React Storefront has it, Create React has it, I believe Gatsby does it for you as well. Almost every single library does it. Some modules require a slightly different syntax. The most significant or popular among them is Lodash. So if you want to cherry pick from Lodash, you need to use that syntax there. If you're creating your own packages, you need to make sure you specify what are called side effects so that Webpack knows and can be a lot more smart about what it includes and doesn't include. And if it doesn't appear to be working, one of the common gotchas is Babel may be turning your ES imports into common JS imports, which don't work with code splitting. With tree shaking. Okay, let's talk about code splitting, another way to get your bundle sizes smaller. So kind of the naive bundle for a React app, say it's an e-commerce, has the home page JavaScript, the category page JavaScript, and the product page JavaScript all bundled into one app. When you go visit that home page, you're downloading all the JavaScript for all those other pages, even though you're just trying to visit the home page. I haven't decided if I'm going to go to those other pages. So what code splitting does is it lets you break the JavaScript bundle apart into these things called chunks that you can then progressively send to the user as they navigate your site. So you can break actually on a component boundary, or you could break on a page boundary. So what this might look like is this would be, say, kind of a child component being rendered by a parent. And if you wanted to code split it and you wanted to do it manually, which is not what you typically do, it would do something like this, which is you use state to keep track of when that child component is imported. And you use this statement right here, which is a dynamic import. And when Webpack sees that, it knows that it's going to have to take that child and split it into a separate chunk. And when that child component finally does import dynamically, you then save that in your state, and then you render appropriately depending on whether it's there or not. Now, in practice, you don't write all that wrapper code. You usually use a higher order component library to do this for you. A higher order component is a function that takes another component and transforms it or wraps it into something else. So in this case, it takes a regular component and it turns it into a code split component. So here I'm creating a hypothetical higher order function called import dynamic, and it does all the work for you and just kind of can use that component like you normally would. There's a bunch of libraries that provide this. React.lazy does code splitting, but doesn't work with server-side rendering. React Loadable is a library that's also been historically popular, although it appears to not be maintained. Loadable components, which is recommended by the React.js docs, if you want server-side rendering. We use React Universal Component, which is very similar. Okay, server-side rendering. So there's really two forms of rendering for an app. The kind of naive approach is client-side rendering, and it's that process on the left. So the browser, runs your app's JavaScript that it gets from the server. There's almost no HTML. And that app JavaScript then creates the HTML that populates the page, and then the browser renders that, and it's viewable and interactive for the user. Server-side rendering is a more complex process on the right, but has some performance benefits. So ahead of time, the server is going to generate the HTML from your app JavaScript. The browser will then download your page HTML from the server. That page HTML will then be immediately viewable or almost immediately viewable to the user because browsers are really good at rendering HTML. They've had 2-3 decades of work on how to optimize that. It can do all sorts of look ahead like image fetching and stuff like that and render the page out. And then it'll run the app JavaScript from the server, but rather than replacing the HTML that's already there, it's going to bind the event handlers to that existing HTML in a process called hydration, and now the page is actually interactive to the user. So one side effect of this is we've slightly split apart when the page is visible and when it's interactive, but the end result is you actually get a faster viewable page for the user. Because the browser no longer has to wait for JavaScript to be fetched, downloaded, and run before it even displays anything that is meaningful to the user. The other key benefit, especially for large companies in publishing and e-commerce, is SEO. And that's because HTML is easier for a crawler to examine and parse than actually having to spin up a headless Chrome instance and run the JavaScript. Now, it's true that at least Google has been claiming they can run JavaScript, and they can. But it's not without side effects. And we do know that Google has this thing called a crawl budget. They're not going to crawl your page forever. And we do know that the way they run their JavaScript is they actually do a 2-pass crawl of your site. First, they crawl it for HTML, and then they have a second pass where they run the JavaScript. And the JavaScript one pass, they've said, is run less often. And it seems to actually be maybe not necessarily as frequent as the first pass. So there's clearly a benefit to running the HTML. It's easier. You're going to use up less of your crawl budget. And think about this. If your page is actually taking a while to run, it's actually eating up your crawl budget simply by being a slow page. So it's actually hurting your SEO two ways. The problem with SER is it's actually really hard to set up. It's especially hard to add to a page or a project if you didn't build it in from the beginning. And don't take my word for it. This is the folks at Spectrum. They're a chat app, open source, that was acquired by GitHub. Here's one of their co-founders. And he tried to do server-side rendering without using a framework and tried to add it to an existing project. And he wrote this blog post. Basically, one of the things he regretted was not choosing an SSR framework from the beginning. What makes SSR so difficult? I'll give you kind of a peek. First is that it requires refactoring what are likely client-side assumptions in your code. So lifecycle methods like component did mount don't run on the server. So if you're doing important stuff in terms of rendering that initial view of the page in there, then that code isn't going to be run when your SSR happens. You got to move that code out. The other thing is you probably have code in there that's assuming window or the document object are available, which are, again, not available on the server. And then other features are finicky and either are hard to work with SSR or they don't work at all. So my recommendation is, use a framework that configures it for you, like React Storefront or Next.js. So here's an example of where that finickiness comes. So this is from alligator.io. He's talking about how to use server-side rendering with React Router. Unfortunately, your node code can't use the logic in React Router to figure out when it gets a request, well, what are the components to render this page? So the solution in this post was really to take your routes and hoist them out of React Router into this other JSON structure that lists out for each path what the components are, just so that node knows what to render. It's kind of like you're no longer really purely using React Router anymore. Another problem is code splitting. And this is an example using React Loadable. Similarly, you need to keep track of which of the code split chunks you are using to render the page as it's being server-side rendered, just so that when you send that rendered page, you have the right chunks that know how to hydrate in the server-side rendered HTML. And so that's what this little code snippet does. And that's really just scratching the surface. SSR, I've categorized it as a performance enhancement, but if you don't do it properly, it can negatively impact your throughput and time to first byte. So here's an example from Walmart Labs. He talks about an SSR rendering process that took 500 milliseconds, which means they could only do at most 2 requests per second for that particular resource. So the way you get around this is you accelerate the feeding or returning of your SSR pages by caching them at the CDN. So what you do is you have a node layer or a backend for front end, and that's going to run your SSR right here. And then you make sure that your CDN is configured to cache your SSR requests at the edge so that you don't have to rerun that whole SSR process and the user just gets a really fast HTML page and you get a really responsive result. The one caveat with this is that you need to make sure your pages are cacheable. And especially in e-commerce and publishing, about 90 to 95% of the page is actually cacheable. But there's like this little 5% that's preventing it. So here, for example, is the item cart count. Another thing that you might have is the user's logged in state. It says like, welcome back, Bob. Another example is something that's personalized, like product recommendations. And so the solution is remove that user-specific data from the server HTML and then late load it client-side. And this is such a common pattern, we built this into React Storefront. So we created a hook called use personalization. And when you use that, it actually goes to your product model. We use MobX, by the way, so this may look a little unfamiliar. But the key thing is right here, where there's a load personalization function. And you can see that when the recommendations are null, we're basically fetching the recommendation data, then populating it, and then storing it into the product model. And then behind the scenes, one of the nice things about MobX, it'll automatically go tell any components that are looking at that recommendation data, they now need to re-render and update the page. So key takeaways about SSR is use it at the start of your project if you can. Use a framework that configures it for you if you can. And then make sure you use caching to improve your SSR load times. Okay, that's a nice segue into CDN and cache management. So I said earlier that speed is a full stack problem. So Steve Souders, about 10 years ago, coined his golden rule of performance, which is that roughly half your performance problems are on your back end and roughly half are on your front end. I would add a corollary. It's actually your front end, your back end, and it's also your CDN. The CDN is actually one of the most neglected areas in your performance that you can actually use to get the best possible performance, as we just saw with server-side rendering. In fact, if you don't have a caching layer like a CDN or an edge, then you really can't use SSR effectively. And if you can't use SSR effectively, you probably can't have a fast time to first paint. Unfortunately, managing your cache can require some complexity. So why is that? Well, sometimes there are things that require custom cache keys. So one example would be internationalization. Suppose you have to support users in French, German, and English. Well, now you need to have French, German, and English versions of every single one, SSR versions of all three of those languages. So you need to split your cache appropriately for that URL based on the user's language, probably based on some type of signal like a cookie. Another example is if you want to filter out incompatible browsers and you know they can't run any of your code anyways, you might want to send them a different version of your SSR page than before. Another case is A/B testing. You might want to have different SSR versions of your page based on the two different variations of your A/B test. By the way, there's a lot of complexity with A/B testing and PWAs, especially as it relates to the service worker. If you're at all curious, let me know, and I'll give you the gory details. Another common problem is normalizing your cache. So to your CDN or your cache, every single URL is unique, means that the content on that page must be unique. It doesn't know that the pages are the same even when they have different query parameters. Or sorry, when they have different query parameters. So in an enterprise, e-commerce context, a really common example of this is a marketing campaign. Say an email blast. Send an email blast to like millions of users, and all of those go to maybe 3 or 4 different product pages, but they all have this individual query parameter so they can track when that specific user clicked that page. Well, that's going to bust your cache. When actually all those users, you're sending a lot of traffic to all the same page. You actually want to increase your caching because it's going to be really advantageous to make those load as fast as possible. So what you want to do is normalize your cache key and tell it, hey, this cache, this part of the query parameter doesn't matter. Now, how you do this depends on your CDN. And the way you control your CDN is through a combination of cache control headers and through your CDN portal. Then there's actually another cache you need to pay attention to, and that's the browser's cache. So you actually have to coordinate 2 different caches, and the way you control that cache is through your JavaScript code. So you've got 2 different caches, but you're controlling them in 2 different ways, and you're trying to coordinate them. So one of the things we thought would help here is this thing we call CDN-as-code in React Storefront. And it lets us control both caches by looking purely at the JavaScript code, and it makes it a lot easier to manage. So here's kind of an example of that. This is how React Storefront's router looks like. It's more similar to Express. But the key lines here are the ones you can see pointing at the arrow. You basically are setting properties in JSON that are saying, hey, enable caching both on the client and on the server, and also set the TTL in this case to 5 minutes. You can also add custom cache keys very easily. So here's a line. You basically add a new property, says key, and you say create custom cache key, and then you can say what you're partitioning on. In this case, say the currency or the language. And these can get really complex. Here you can kind of group them. You can put all the North America users together and all the EU users together. The last thing about caching, we talked about measuring speed. You need to make sure when you measure speed, you measure the uncached as well as the cached. But the real user monitoring equivalent is to take a look at what your cache hit rate ratios are, so that you're basically normalizing those cache keys properly. Unfortunately, that data is either buried in your CDN portal or sitting in some Splunk logs. But whatever you can do some tooling to pull those out and look at them on a periodic basis. And one of the things we actually do in our platform is we pull those metrics from the CDN forward to the front-end developer in the portal so they can quickly look at, for each of their route handlers, what is the cache hit ratio for the most the highest performing and the worst performing in terms of cache hit rate. And it's a really effective way to look at the performance of your site. In fact, you do really good caching, it'll forgive a lot of other sins elsewhere in your code. Okay, let's talk about accelerating browsing speed. So the first technique is using a service worker and predictive prefetching. So the intuition here is really simple. The page that the user is next likely to navigate to has to be one of the links in the page that they can see. So why don't we prefetch the data and the JavaScript needed for those pages ahead of time before the user actually clicks? And so the algorithm for this kind of setup works kind of like this. You first detect when the link is in the viewport. You can use React Visibility Sensor or Intersection Observer on your component to basically detect when your link component scrolls into view. Then signal to your service worker to prefetch the links. And then make sure you prefetch not only the JavaScript chunks that were code split to render that link page, but also the API data as well, if you want to get the best possible performance. And then the other gotcha is make sure you pause the prefetching appropriately so you're not creating a lot of network contention when the user finally decides and commits to where they want to go to next. In React Storefront, this is actually built in for you. There's a prop called prefetch. You can either set it to visible, to only prefetch when the link becomes visible, or you can set it to always fetch it for things like navigation tabs and things like that. One gotcha we've encountered is unstructured CMS content. So if you're in an enterprise context, sometimes the CMS just gives you raw HTML that gets deposited on your page. These can be things like hero images, banners, or promotions. You need to parse that HTML and then make sure those anchor tags are prefetchable. It seems like a minor thing, but actually when you consider that these are used for very important parts of the page, there's a lot of click stream that goes through them, so make sure those are prefetched as well, because they're actually the things that are most likely to be clicked on by the user. There's another form of prefetching based on machine learning, where what you do is you look at all the analytics data, and you determine for a given page, what are the pages that a user is next most likely to navigate to based on historical navigation patterns. And Google Analytics makes this data available to you. Guest.js is an open source library that you can use to incorporate this into your applications. The premium version of React Storefront is called React Storefront Extensions. That also has an integration with it as well. Again, this is a full stack problem. Prefetching without a CDN is deadly. So to understand why, think about a category page that has 10 products on it. If the user scrolls through the page and you're just using visibility sensor naively, you've just triggered 10 fetches to your website in the same time your user normally would have fetched a single page. That's an order of magnitude. That's 10 times more requests to your origin server. So you've basically increased the load on your servers dramatically. So you need a CDN in place to basically take that load off so you don't topple your origin servers. Otherwise, you're going to increase your server costs, or you're going to have high CPU utilization, which either decreases your page speed because it takes longer to respond with TTFB, or you might just totally denial of service hose your CPUs. So make sure your prefetch data is being served by the edge. Okay, the next technique is lazy loading. So this is a surprisingly useful technique in speeding up client-side transitions. Basically, you're telling React, only render the stuff above the fold as we navigate forward, and then you save the stuff below later. Images are really important because they can be a lot of them, especially, say, on a category page, and they create a lot of network contention. So you want to not have them interfere with the stuff that's above the fold. And then you can have some components that are expensive to render. Maybe they're doing a lot of calculations, or maybe there's something like recommendations. You want to save those to later, move them below the fold, and set them as something that happens later. Also, not on the slide, client-side A/B testing can sometimes interfere with your rendering. Another great place to put in something in lazy rendering. There are a lot of different ways to do it. In React Storefront, it's built in. For images, there's a lazy attribute to enable it. You can go look at the source code for how it's implemented. Chrome is actually shipping now with lazy loading for images built in, so it makes that implementation a lot easier. You can actually just do it out of the box. We also have a lazy component that we use to wrap really slow components. to lazy load them. But make sure if you do something like this, you build into your API for it that you specify what the final layout height is so that the page doesn't jump around when that lazy loaded stuff finally appears. Otherwise, you'll get what's called poor layout stability. And poor layout stability is one of the dead giveaways that a website feels like a website, that kind of jank. Whereas when you compare to like a native app, it feels very solid because nothing usually jumps around in a native application. Okay, skeletons and data reuse. Skeletons, I think Facebook probably popularized this the most. It might be a little bit hard to see in this image. There are those on the projector. There are these gray bars, right, that you show kind of in between the loading state while you're busy fetching data from the network. And although you're not actually speeding up the transition, you are improving the user's perception of load time. And sometimes in significant ways if you use data reuse. So, because often the page you're navigating from has some content that you can leverage in the transition. And in e-commerce, this pattern happens a ton. You've got a category page, and then you've got a product page. And there's a ton of stuff here that we can leverage from the existing page as we navigate to the next one without even a network fetch. So first of all, we know what the breadcrumbs are going to be right here. That's pretty straightforward. We know what the title of the product is. We can put that up here. And then we don't have the full-size image. That would pull down a lot of bandwidth. But we do have a thumbnail version that we can display right here while we wait for the full-size one to show up. And so we're kind of progressively drawing. So basically about 90% of this page we can actually render without even having a network fetch. We might even have that style if we've got it in the metadata that we got from the fetch that populated this product category page, rather. So skeletons are so useful in React Storefront. We built them in as a library of components. We have a series of skeleton components you can see here that allow you to create basically blank rows. Not that sophisticated, but we also built in the capability for data reuse. So the way this would work, at least in React Storefront, is you decorate onto your link components. You give them the data that they're going to need for the page they're going to navigate to. And then inside that skeleton, you can see you can pull out of your props the information that was passed into link. And you can leverage that reuse data here, for example, on the title, right in the rendering of that skeleton. And you can set this kind of thing up in your application as well. Minimizing unnecessary renders. Let's see how we're doing on time. Yeah, I'm going to go through this one really quickly. Use React DevTools has a setting in the DevTools Chrome extension for React that lets you highlight the screen whenever renders happen. That's a good way to find and capture them. If you need to optimize your rendering, look at using pure components or supplying a component should update function to tell React when it really should or shouldn't update. If you are migrating it to hooks, keep in mind that your components are going to rerun every time their parent state changes. And that can be really wasteful with function components. So use a technique called memoization, using either react.memo or the useMemo hook. You can Google for that. We don't have enough time to put it into the deck here. But the one takeaway that is less common, and the recommendation I'll give, is consider using MobX for your state management. It automatically handles a lot of this for you, and components will only re-render when fields they observe change. So it makes things a lot easier, and that's what we use in React Storefront. Okay, last thing is AMP, Accelerated Mobile Pages. Accelerated Mobile Pages is a subset of HTML formalized by Google that gets preferential performance benefits when you're navigating from a Google search results page. So here's an example. This page loads in basically 300 to 400 milliseconds. If you blink, you will literally miss it because the eye blink is like 300 to 400 milliseconds itself. You're going to spend more time waiting to watch the change than it actually happens. And AMP pages load instantly. Part of the reason for this is AMP has some restrictions on what you can do inside an AMP page in terms of CSS, sizes of the CSS and what you can use, also around the JavaScript you can run. But one of the most significant things it does is it prefetches the document. It does that visibility prefetching. Under the hood on the Google search results page, before you even click the link, it's actually fetching the pages that are in the links, the data for the pages that are visible links, and rendering them behind the scenes in a hidden iframe so that when the user clicks the link, either they have the data or it's actually even just in the iframe and they just need to show it to you. And in a sense, we've come full circle. Because I said earlier, the best techniques you aren't using are proper cache management, server-side rendering, and prefetching, because they will forgive a lot of sins elsewhere in your React app. AMP kind of does the same. AMP does prefetching. AMP does a form of server-side rendering when it's served from the Google cache, and it's served from Google's own cache, so it's cache management again. It's actually, AMP is some of those best practices, again, just in the context of the Google search results page. Now, there is some misunderstanding out there about the performance of AMP. You will see people say, I can build a site that's faster than AMP. And they're not entirely wrong. What they're doing is they're sticking, the AMP version of a page in Lighthouse, and they're sticking the non-AMP version of the page in Lighthouse, and they're comparing the performance. The problem is that the natural habitat of an AMP page is from a Google search results page. And it gets preferential loading, gets that prefetching. It's actually a browsing speed transition, one of the things we talked about earlier, which you cannot measure with Lighthouse. You need to use something like web page test. If you actually do it in web page test and look at the film strip, you'll see hey, that's really fast. And it's really hard to get faster than that because by prefetching, they've gotten rid of the network effect. And so that's what gives you really that instant speed. So AMP really needs to be part of what I'd call a holistic speed strategy. And if you're in, say, a vertical like e-commerce or publishing, well, I can tell you in e-commerce, 50% of your organic traffic is coming from search. So even though it seems like a lot of overhead to have an AMP version and a PWA version, it certainly is worth the money, worth the effort. So what your user flow looks like is if a user comes from search, they go to the AMP search result, that's a browsing speed transition, and then while that AMP page is being browsed, you're actually bootstrapping up your PWA resources so that the next transition is also a browsing speed transition and can load really fast. And then once they're on your PWA, the rest are all client-side rendered and also browsing speed transition. So that whole top navigation for 50% of your traffic, say if you're in e-commerce, can be browsing speed transitions where we can break that 1 second barrier a lot easier than if we're trying to do it from a regular page transition. Now, if somebody's coming in through another channel, like one of these ones here, you still need a server-side rendered page to get the best possible first load experience. The problem with this is that AMP is almost a completely separate format. You have almost no to minimal JavaScript. They just released AMP script recently, so you can do some JavaScript. PWA is almost exactly the opposite. It's almost all JavaScript. So it can kind of feel like you have to recode your site twice. So to manage AMP at kind of an enterprise scale, what I recommend is you actually set up a pipeline to automatically convert your React code base into AMP. And that'll spare you some of that tedious work. And then I would also recommend that you build in AMP validation into your CI/CD. Because if you're building an AMP page but it's not AMP valid, you're basically throwing your work away. Google won't prefetch it because it can no longer make the performance and security guarantees. It'll take it out of the Google cache. You also need to be careful. Again, like a merchandiser or a marketer doesn't add CMS content that breaks your validation. And one of the things we actually do in our platform is we actually go and look for those invalidations created by images that don't have the height and width specified, examine the image and put that data back into the content so that it doesn't violate AMP validity. And then finally, tracking analytics with AMP can be difficult because you're switching domains based on how AMP works. So you need to use this thing called session stitching. So you're probably wondering how to automatically generate AMP from your PWA. It's not easy. I don't think we have time to go into it in detail, but there's a blog post you can Google for how we do it. It's built into React Storefront extensions, but we talk about the process by which we do it, and it's built in for you if you use React Storefront extensions. Okay, so I opened by saying these are the 4 key things I want you to know, and I'm just going to repeat them here to make sure you walk away. That's the key message. And that speed, again, is the #1 value proposition for PWAs. You're probably measuring site speed wrong. Make sure you're looking at browsing speed. Make sure you're using perceptual metrics. If you want to solve speed in the best possible way, it's going to take full stack coordination from front end, back end, and crucially, the often forgotten CDN. And then the best techniques that you probably aren't using are proper cache management, server-side rendering, prefetching, and AMP. They'll forgive a lot of flaws elsewhere. One more thing. So I've talked a lot about our framework, React Storefront Extensions, which is open source. But we get a lot of feedback from folks when we talk to them about it. And the other really popular server-side rendering framework for React is Next.js. In fact, I had a conversation with somebody today, and when he heard about what we were doing, he's like, oh, that's really interesting. Do you work with Next? And we get that a lot. Next is clearly very popular, so I'm excited to announce we are hard at work on the next version, no pun intended, of React Storefront, and that will support compatibility with Next.js. So look for that before the end of the year. We're really excited to roll that out. Okay, that's it. Thank you.